Shri Gurubhyo Namaha, children. Today we are moving on to another important and interesting topic in current electricity, which is meter bridge. Right now, this meter bridge is an example. Now, the working of Wheatstone's network, which we were discussing in last class. Now, this meter bridge is one of the application of Wheatstone's network, like where we were discussing about four resistors, and when you have a galvanometer in between at a particular point, the galvanometer shows zero deflection. Then we saw that the ratio of R1 by R2 is equal to R3 by R4. So this is what we were discussing in Wheatstone's network. So the application of it is meter bridge, which we are going to learn today. Again, this is a practical experiment for you children, meter bridge, where we are going to learn exactly, completely how it is just a form of Wheatstone network, right? Now let us go to the structure of a meter bridge. Now this is the meter bridge. Now this consists of a wire of length 100 centimeter. Now here is the wire A and C. See here the length of this wire. The length of this wire is 100 centimeter or 1 meter. Okay, 1 meter. And this wire is fixed between 2 points A and C. Okay, it is taut. Taut means you cannot, it is held fixed, okay, in between A and C. Okay, right. Now there is a metallic strip here. Now see here, this is a metallic strip, now in the form of a L-shaped metallic strip from the wire. Now here you have L-shaped metallic strip from A, and here you have an L-shaped metallic strip from C. Okay, so two metallic strips, and these metallic strips has two gaps. Now here between these two, now this is also a metallic strip. Now in between these two metallic strip you have a gap G1. Let me name this as gap G1. Now here let me name this as gap G2. Okay. Now in between these two gaps you connect a resistor which is considered to be an unknown resistor whose value you are going to determine. So that unknown resistance whose value you are going to determine is connected across this gap G1, and the known resistance which we are going, now here we can adjust this value of known resistance. You have a resistance box in the lab, you can adjust the value of resistance and fix whatever value of resistance we have to keep, that can be fixed. Now this is called as a known resistance. Now that known resistance is kept in this gap, is fixed in between the gap G2. So G1 you have unknown resistance connected, and G2 you have the known resistance connected. Okay. Now again you have a point in this metallic. Now this has got 3 points children. Now the 2 points are connected to the known and unknown resistor. Now the middle point here you have a terminal. This is connected to the galvanometer, and the galvanometer is connected to what is called as a jockey, metallic jockey. Now this jockey, it is a pen type, like how the pen is like this. Same thing, you have a metallic pen like thing which is called as jockey. Now you have the wire connected to the jockey, and you can move this jockey along the metallic wire which is AC. Now this jockey can be moved along this metallic wire. So this jockey makes connection with the wire from the external. Now this is the external circuit, right? You have a resistor, you have an unknown resistor, you have a galvanometer. Now all these are connected to the meter bridge through the jockey. Okay, so this is the construction, right? Now page number 120 you take children. The first paragraph talks about the construction. Look at the explanation there. The meter bridge is shown in the figure 3.27. It consists of a wire of length 1 meter and of uniform cross section area stretched taut. Taut means tight, and clamped between two thick metallic strips bent at right angles as shown in the figure. The metallic strips has two gaps across which resistors can be connected. So these are the two gaps I was talking about. Now let me write this as gap G1 so that you will understand it clear. Okay, so this is gap G1 and this is gap G2. Okay, now which resistors can be connected? The end points where the wire is clamped are connected to a cell. So here, from here you connect it to the cell. Okay, now this may be a Leclanche cell which will be connecting in the lab. Okay, a cell and a key. So A, that is the positive terminal of the cell is connected to end A and the negative terminal is connected to C through a key. Okay, right. So the end points where the wires is clamped are connected to a cell through a key. On one end of the galvanometer is connected to the metallic strip midway between the two gaps. So here from this you connect it to a galvanometer and the other end of the galvanometer is connected to a jockey. And as I told you, the jockey is a metallic rod and one end of the jockey is a knife edge which can slide over the wire. So the jockey can slide over the wire. It can make connections with the meter bridge wire. Okay, so capital R is, what is capital R? Capital R is an unknown resistance. So let me write here. Capital R is unknown resistance, whose resistance we are going to find out, and S is the known resistance. Okay, ma? Right. Now, how this meter bridge works? Right? Now let us fix a known resistance. Okay, let us fix a value of known resistance. Now, before starting the experiment, we should check whether the connections are correct. For that, you need to keep the jockey wire near the terminal A. Now, if you are going to keep the jockey wire near the terminal A, the galvanometer shows deflection on one side. Okay, then you move the jockey to the terminal C. So when you keep the jockey in terminal C, again immediately galvanometer will move to the other side and show the deflection on the other side. So when the deflections are on either side, then you can say that your connections are correct and you can proceed with the experiment. So this is the first thing you should do before starting the experiment. You should check for the deflection in the galvanometer on either sides when you keep the point at A and C. So then you can proceed with the experiment. To start with, we'll fix a known value of resistance. And after fixing the known value of resistance, we have to move the jockey from A. So when you keep moving the jockey along the wire, now you will have deflection in the galvanometer. So you start keeping the jockey from here. Initially, as I said, there is a deflection to the left side of the galvanometer. Suppose if the jockey is here, the galvanometer deflection, now this is the galvanometer, the deflection will be to the left side. Now you keep on moving the wire, moving the jockey along the wire, the deflection will start increasing and at a particular point, at this point which is called as D, the galvanometer will show zero deflection. In the sense, the galvanometer, that pointer needle will be pointing towards zero. So look at my hand, children. Initially, when you keep the jockey on the terminal A, this will be the deflection. When you keep on moving the jockey over the wire, the galvanometer, the reading keep on increasing, and at a particular value, the galvanometer show zero deflection. So at that point, which is D, you have zero deflection, which means the potential at this point will be the same. As far as this connection is concerned, there is a current that is flowing from the cell from here. The current at this point, okay, at this point there will be a current flow, and then the current will be going this side also. There will be a current flow. At a particular point, the potentials will be the same. If the potential is going to be the same, now this will be the resistance. Now this AD will be the resistance and DC will be the resistance. You remember the Wheatstone's network. I'll just draw a rough here. So this is how the Wheatstone's network was. In between you have a galvanometer. Now you have P, Q, R, S, and we proved that P by Q is equal to R by S, or resistance upon R1 by R2 is equal to, we proved it to be R1 by R2 is equal to R3 by R4. This is what we did. Or R2 by R1 is equal to R4 by R3. So here all the resistance will be the same at this point, and AD becomes resistance and DC also becomes, so you have 4 resistors. It is exactly resembling the network of a Wheatstone. So this is one resistance, this is one resistance, and AD becomes the other resistance and DC becomes the other resistance. So at that point the galvanometer will show zero deflection. Is it clear, children? Are you able to understand? Now we can measure this line. Now this is a 100 centimeter wire. If this length is going to be 30 centimeter, naturally DC will be 70 centimeter. So we can find out the value of the unknown resistance. Now this value is already known. Now this value I can measure. This value also I can measure. With all these values I can find out the value of the unknown resistance. This is how a meter bridge works. Is it clear, children? Yes. Now take the second paragraph. The second paragraph explanation. Look at the explanation, children. Now R is the unknown resistance. So what is R, children? Try to understand the concept clearly. R is unknown resistance, and across another gap you have a standard resistance which is S. Okay. Now you connect the jockey to some point D on the wire. Now this D is at a distance of L1 centimeter from the end A. Now L1 is nothing but L they have given, and the value of L is given as L1. Okay. And the portion AD of the wire has a resistance. Now what is the resistance of this? The resistance of this is L1 into R. And what about the resistance of this? This is 100 minus L1 into R. As I told you, if this length is going to be 30 centimeter, now 100 minus 30 will be 70 centimeter. So it is 100 minus L1 into R will be the resistance of this DC. Is it clear? So the portion DC of the wire has a resistance R into 100 minus L. The portion AD of the wire has a resistance R into L1. So there are 4 arms now. One is AB, and here BC, and AD and DC. Is it clear, children? Yes? Now, so if the jockey is moved along the wire, at one position the galvanometer will show no current. No current means the galvanometer will point out zero deflection, right? So we can write the formula R by S. R by S is equal to R into L1 divided by R into 100 minus L1. So here RR gets cancelled. So here I have R by S equal to L1 by 100 minus L1. So this R is the unknown value. So to find out the value of the unknown resistance, I can rearrange this formula, and with this known values I can find out the value of the unknown resistance using meter bridge. Is it clear? So this is the balance point, or this is the balance condition where the galvanometer will show zero deflection. And we know that resistance of any conductor will depend upon what? It depends upon the length of the resistance. You have read already when we talked about resistance, there are 3 major factors on which the resistance depends on. One is the length of the conductor. From this only we derived Ohm's law. Hope you remember. Resistance depends on L. So what will be the resistance at this point, which is given as R into L? Is it clear, children? So R into L. So resistance depends on length. So if this is going to be a wire, this wire has definitely got a value of resistance, and depending upon where the zero deflection is, that length is taken. So it is L into R here. Are you able to understand? So with this we can find out the value of the unknown resistance using a meter bridge. Is it clear? So this is about meter bridge, and you have numericals based on this. Now this numerical is from your textbook, children, page number 128, question number 3.10. Let us read the question. There are 3 questions there in this sum. In a meter bridge, the balance point is found to be at 39.5 centimeter from the end A when the resistor Y is of 12.5 ohm. Determine. Now look at the diagram. They have given the diagram also, children. Listen here. Now this is X. Okay. Now AD length is given as 39.5, and with the resistor known value. Now this is known value. Now X is R and Y is S. Okay. So the known value of this resistor is given as 12.5 ohm. Determine the resistance of X. Why are the connections between resistance in a wheatstone or meter bridge made of thick copper strips? I'm going to explain that. Now let us solve the sum first. So the value of L is given as 39.5 centimeter. Now as far as this diagram is concerned, X is equal to R, children. Okay. And Y is given as S. So S is equal to Y, and this value of Y is given as 12.5 ohm, children. So what is the formula? The formula is S is equal to 100 minus L by L into R. So substitute. S value is given as 12.5. 12.5 is equal to 100 minus 39.5 divided by 39.5 into, I need to determine the value of R. So rearrange this formula. So R will be equal to 39.5 into 12.5 divided by 100 minus 39.5 is 60.5. So when I simplify this, I have the value of the resistance to be 8.16 ohm. Okay, so this is the value of the unknown resistance. Now, why do we connect copper strips? Because now whenever we make connections by thick copper strips, it minimizes the resistance. So that's why we use minimizes the resistance of connections. Now all the connections are connected to metallic strips, right? So they also have resistance. So to minimize that, we will connect it by thick copper strips. So this is the answer. Copper strips minimizes the resistance of connections. Okay, so that is the first one. Okay, so look at the second question now. Determine the balance point of the bridge above if X and Y are interchanged. So now X and Y is going to be interchanged. So in that case, R becomes Y now, which is 12.5 ohm. Then S becomes X now, which is equal to, what is the value we found out now? Now this becomes 8.16. Now what I have done, you are able to understand? I have just interchanged X is equal to R and S is equal to Y. Now here R becomes 12.5 and X becomes 8.6. Okay, now the connections are, now the resistances are interchanged. Now I need to find out the balance point of the bridge when X and Y are interchanged. So in that case, again I will go for the same formula. S is equal to 100 minus L by L into R. So S becomes now 8.16 equal to 100 minus L by L. This is what I should find out. I should find out the balance point into, what is the value of R? R becomes 12.5. Now simplify this equation. This L goes this side. So it is 8.16 L equal to 100 into 12.5 minus L into 12.5. Correct? Now this will become 8.16 L equal to 100 into 12.5 becomes 1250 minus 12.5 L. So bring this 12.5 L to this side. So both gets added up. I will have 20.66 L equal to 1250. L becomes 1250 divided by 20.66, which is equal to 60.5 centimeter. So this is the balance point. Okay. Now one more question is there. What happens if the galvanometer and cell are interchanged at the balance point of the bridge? Would the galvanometer show any current? If the galvanometer and cell, which means here this galvanometer is replaced by a cell and the cell is replaced by a galvanometer. So in that case, will there be a current flow in the circuit? Yes, definitely there will be a current flow in the circuit, because when it is interchanged also, definitely the balance bridge condition can be achieved. That is very important. If both are interchanged also, there should be a balance bridge condition, so that the resistance will be the same. So that can be achieved if you replace cell and galvanometer. So definitely there will be a current flow in the circuit. So that is the answer you should write as sentence. If the galvanometer and cell are interchanged at the balance point, the condition of the balance bridge is satisfied, and hence the galvanometer shows deflection. Okay, ma? So this is about the problem. Next we will solve a simple problem, children. This is example 184. This is not there in your textbook. Okay. In meter bridge, the null point is found at a distance of 60 centimeter from A. So in the first case we will write R by S. So in the first case, R by S is equal to, if the from point A, if it is going to be 60, then L2 will be 100 minus 60, which is 40. So it is 60 by 40. Now this I can simplify. This will be 3 by 2. Now this is my equation 1. Right. If now a resistance of 5 ohm is connected in series with S, the null point occurs at 50 centimeter. So in the second case now, that is a case they have given, they have increased the resistance, known resistance 5 ohm. If it has been increased by 5 ohm. So in that case, I have R by this S plus 5 I have. Okay, so S plus 5. Now this is equal to, the null deflection occurs at 50 centimeter. From A it is 50 centimeter. So numerator I have 50, denominator also I have 50. So this is my second equation. Okay. Now question is, determine the values of R and S. So divide 2 by 1. So 2 divided by 1. So when I divide 2 by 1, I have not 2 by 1, sorry children, 1 by 2. 1 by 2. So let us divide R by S by R by S plus 5 equal to, the right side you have only 3 by 2. So when I simplify this, I have S plus 5 by S equal to 3 by 2. Now when I simplify this, I will get 2S plus 10 equal to 3S. So I have minus S is equal to minus 10. So S is equal to 10 ohm. So I have found out the value of S. Now with this I can find out the value of R. So I take this first equation. First equation, what is the first equation? R by S is equal to 3 by 2. R is equal to 3 by 2 times of S. When I substitute 3 by 2 into 10, I have 15 ohm to be the value of R. Is it clear, children? Yes. So these are some of the problems that I have solved based on meter bridge. Now so many concepts we have discussed. Wheatstone network followed by meter bridge. Both are considered to be very, very important topics, children. Please go through the topics and work out all the numerals. Okay, ma? See you, children.